Hello everybody. We're still talking about the packed column, and in this video we are gonna start talking in details about the packed column. In the previous video we were giving more of an introduction to the background of the mass transfer equations that we're gonna use, but in this video it's gonna be concerned more about the packed column in more detail. So before going into the equations and in these things, I'd like first to take a look at the packed column from inside. So we know that the packed column contains packing, but we don't know, or some of us might not know, what is this packing. So this packing is just a solid material that is put inside the column, and it takes many shapes, or there are many shapes. The one of the very famous shapes is the bird saddle. So it looks like the saddle of the horse, so it's called bird saddle like for this reason. There are like cylindrical shaped packing materials like the Rashik rings, the pole rings, and there are many other shapes that are used. They are randomly put inside the column. By randomly, I mean that they are not like put like Lego parts one by one. They're just put in random distribution. As you see here, some of these pole rings are put like horizontal, some are vertical, some are at an angle. So it doesn't matter. They are randomly put inside the column, and that's why we call it a random packing. And as you see, there is a liquid going down and there is gas going up, and they're offering a good contact between these two things, the two phases. The other kind of packing is called the structured packing. So instead of having this as small particles or small packing materials that are put inside the column, which might have some disadvantages. For instance, there is very high pressure on the particles in the bottom, and this makes it more susceptible to being or to breaking or to shattering due to this high pressure. And of course, it takes longer time for filling and discharging in the column or from the column. But for the structure packing, it's like as you see, it's a single part. It's made or it's custom made so that it's already ready for being put in the column. And as you see, it's porous and it offers a flow like place for the two liquid and the vapor streams to go up and down, and offers a good mass transfer between them. So there are two types of packing that are used in industry. And now let's talk about the like the important information that we need to know about the packing. So the packing, as you all would expect, it's just a material that we put. It's an inert material. It's not like a catalyst. It does not take part in a reaction or something like this. It's just an inert material that offers a large surface area for the two materials or the two streams to interact and to offer the area enough to make the mass transfer that we are interested in happen. So one of the parameters that's specific about the packing material is the specific surface area, which means that or represents how much area that one unit volume of this packing material offers. So let's say I have 1 meter cube, and I know that this packing material has a specific surface area of, let's say, 10 meters square per meter cube. So each meter cube of this packing material offers me 10 meters square of area. And of course, as it gets bigger, as it's more favorable for me, because as the area increases, as the rate of mass transfer increases, and then I would require less height or less amount of this material. So the total area of mass transfer would be the specific surface area multiplied by the volume. If you multiply this by a volume, it's gonna be a surface area. So it's kind of simple. So this is the surface area of the column multiplied by the height. So this is the total volume of the column. And you see, this is the Z and this is D. Actually, calculating or estimating the specific surface area of a column or of a packing material is not an easy task. That's why we usually use the parameter that's called the volumetric mass transfer coefficient, which is the multiplication of the mass transfer coefficient and the specific surface area. Both are two parameters that are hard to estimate or hard to calculate, and we will see in the calculations in the next or the coming slides that these two are always together in the equations that we're going to use. So instead of estimating each one of them separately and getting a high error that's going to be multiplied by multiplying these two parameters together, we can simply consider them as one parameter and calculate both as one single parameter, which is called the volumetric mass transfer coefficient. And of course, it's going to have the units of moles per second, meter cubed of packing per mole fraction, because it's KY. Now let's, before going into the calculations or the derivation of the equation of the packed column, I want to quickly revise the solute free bases. We used this solute free bases previously because when we were discussing the tray column, we had to simplify the process for us so that we can draw the operating line in an easier way, and that's why we used the solvent free bases so that the operating line is a straight line. We will need it here, but not for the same reason. But this is just for the sake of revision. The solute free bases flow rate of liquid is the flow rate of the solvent excluding the solute, which is going to be the total flow rate multiplied by y minus x, 1 minus x, and the same for the vapor. It's going to be v multiplied by 1 minus y, where x and y are mole fractions. And for L dash and V dash, we use the mole ratios, which is the mole of the solvent per mole of the solute per mole of the solvent, which can be calculated from the mole fraction from this equation, x divided by 1 minus x. The same for y, it's y divided by 1 minus y. And as we said, x and y are mole fractions. The uppercase x and uppercase y are mole ratios, and we can and the total flow rate is calculated from these two equations. Or I mean the flow rate of the solute can be calculated from these two equations, L dash x and V dash y. We can calculate the mole fractions from the mole ratios. It's going the other way from this equation. It's x lowercase x equals the uppercase x divided by 1 plus uppercase x. I'm sorry. So these equations are already discussed before, so I'm not going to go into more details about them. I just want them to be in your mind because mainly we will use this equation in the following slides, and we will use these equations in the calculations of the tray column when we go to Microsoft Excel. So it's better to kind of refresh your mind regarding these equations. Now for the packed column, we agreed that this is a distributed parameter system, and that's why we are going to do our calculations or the governing equations on a differential height of the column, and then we will integrate over the whole height. And this is what we're going to do. It's going to include some mathematics and some mathematical manipulations, and that's why I don't want you to feel like bored or anything. I don't want you to be like fully aware of all these steps. I just want you to understand how we reach the final equation. So this is my whole point of this. So the flux, we mentioned in the previous video that the flux can be calculated from this equation for the gas phase and from this equation for the liquid phase. And we said that 1 minus YA is the logarithmic mean between the bulk and the interfacial concentrations or the mole fractions. So this is the equation that we are going to use. We said that both are equal because we are in a case of a steady state. So the flux going into the interface is the flux coming out of the interface from the other side, from the gas to the liquid. So if we multiply this by dA, which is the differential area, differential surface area of mass transfer, then this is going to be the shape of the equation. We have AS dz, which is the specific surface area. This is the cross-sectional area. We are used to call it A, uppercase A, but I think because we have dA here, the author of the textbook didn't want to confuse the reader, so he called this S. So this is the surface area of the column, which is pi over 4d squared, which is this S. So A multiplied by S multiplied by dz is going to give us the dV. I should have split it, but I hope you understand it. So just look at this and this. The only difference is AS dz. So AS dz is the dA, which is the A multiplied by dV, which is the small a multiplied by dV, which is S dz. And the same for here. So we have two equations for the mass transfer rate in the in the liquid phase and in the vapor phase, which are these two equations. The rate of mass transfer also, on the other hand, we can look at from the other side, is equal to the change of the flow rate of the solute and of the liquid and the change in the flow rate of the vapor, which is logical because it's the solvent is going to be constant. It's going to gain more solute, and the gas is the same, and it's losing more solute. So the change in the volume, we should have a negative sign here, but the change of the flow rate of the solvent and the change of the flow rate of the gas are equal, which equals to the rate of mass transfer, by the way. So we can differentiate this. We say that's dVya, and we have two variables that are or the two parameters are not constant, so we can make it easier for us to differentiate them by making one of them constant, which is the V. So I can substitute by the V by the solute free basis, which is the V dash divided by 1 minus Y. So this is equal to this V, and this is multiplied by Ya. Now V dash is a constant, so I can get it out of the differentiation, and I will end up with d of Ya over 1 minus Ya. The differentiation of this term equals dya over 1 minus 1 Ya all power 2. And I can now reverse what I did. So I'm gonna take V dash over 1 minus one minus Ya and put it as Y, and then I'll end up with dya over 1 minus Ya. So this is the same here, it's NAdA, which is equals to the same thing that we mentioned in the previous slide. This was NAdA. So we have two forms of NAdA now. And now we can put them together. So V multiplied by dya over 1 minus Ya, which is this, equals to this term from the previous slide. Now it's getting more simple. Now I have only dz and dya. So this is the dependent parameter, and this is the independent parameter. So I'm gonna separate the variables. I'm gonna put the equation in a form where I have dz on one side and all the other parameters on the other side. This can be applied for the liquid phase, so we can do it this way as well. And with simple mathematics, I can put dz on one side, and then it's gonna be the total height of the column. This is the goal that I'm aiming at from the very beginning. That the height of the column is gonna be the integration of dz from 0 to z, which equals to the integration of L over K dash XAS multiplied by this thing that contains a lot of mole fractions, dxa, and the same here for dya. So as you see, this is just an integration, and the rest is going to be just mathematics. But one thing that people do as a simplification in case of like low concentration of the solute, if you have dilute solute in the vapor phase, we can assume that these two terms are constant. So the L is going to be almost constant if the x is small, and the dependence of K dash and X and K dash Y on the solute is concentration is not going to be very high. So these two parameters, or these two like terms, can be considered as constant, so they can be kicked out of the integration, and we will end up with just integrating this term and this term. And in such cases, these are considered as the height of transfer unit. So these have the units of length, and this is called the transfer unit, which is kind of corresponding to the stage in the tray column. And then the rest of the term, which is the integration of this part, is going to be called the number of transfer units. And the total height is considered the height of transfer unit multiplied by the number of transfer units. So this is one method of doing the calculations. It's going to be almost the same, or very, very close to what we're doing, with just making it simpler by considering these as constant parameters, which is not the case in many cases. So the general and the more accurate way to doing this is to do the integration. But I just wanted to highlight this so that in case you hear this term, you understand what we mean by the transfer unit in a packed column. Now let's see how we can do the calculation. So what we're going to do is simply do graphical integration. So we will put the equation as a form of function of Ya dya, where the function of Ya is this whole thing. And to do the integration, we need just to like split the y into like many parts. So let's say I'm going to split it into 5 or 6 increments or whatever, 10, 20, whatever thing. Of course, as you make it more, you're going to make accurate calculations, of course, but it's going to be tougher for you to do the calculations. But this is what we're going to do. We're going to assume values of x and y with increments from the y1 to y2, which is the feed concentration to the outlet or the outlet concentration to the feed concentration in the gas phase, and we will calculate y, and then we will calculate k dash x and k dash y. So this is what we are going to do in Excel. I want to put it here so that you have kind of expectation of what we're going to do in the Microsoft Excel when we do the calculations. So all what we're going to do is just to get the values of these terms so that we can fill this table and get f of y. And then using the trapezoidal rule, we can calculate the z. So what we are going to do is first calculate or assume or get the values of x and y from the operating line equation, then calculate k dash x a and k dash y a, and then calculate x interface and y interface. And this is going to be like a challenging thing because, as we said before, this is a trial and error calculations. So you're going to do this for many terms, and this is what I'm going to do. I'm going to use macros to make it simple for us. And then you calculate the liquid and vapor flow rate. So now you know all these terms here, and then you can calculate f of y, and using the trapezoidal rule, you can calculate the total height of the column. This will require knowledge of different things. We will, or we need to know the equilibrium relation. As y as a function of x as an equation, because this is how, or one of the things that we need to calculate the x interface and y interface. And we should have formulas to calculate the k dash xa and k dash ya, and this is one thing that we'll see as well. And we should know the cross-section area of the column, which is something that we didn't need before. So as you see here, the approach of solving the packed column is totally different from the approach of solving the tray column. And I hope it's clear why we had to go through this. The nature of this system is different from the nature of the other, and that's why we had to go through a different route so that we can put an equation that describes the system in a proper way. So that's all for this video. I'm going to see you in the next video, inshallah, where we are going to see how to do these calculations in Microsoft Excel. So I'll see you then. Goodbye.